Yesterday, an image dropped that should not exist, and it sent the astronomy world scrambling. 3i Atlas appears to be breathing a narrow jet straight toward the sun, when every rule says jets should be shoved the other way. If this is real, something about small icy worlds near a star works very differently than we thought. If it is a trick of processing, we are chasing a ghost. So which is it? Here is where the story gets strange. We are going to test it, step by step, in public. Join the investigation, tap like, subscribe, and stay with me through the twists ahead. Picture the scene in your mind. The brilliant core of the object is masked to keep the glare from drowning everything around it. A soft halo of gas and dust spreads outward, the classic coma you expect from a lively comet. Then a faint, focused plume stretches for roughly 6,000 kilometers, not away from sunlight but toward it. That single detail turns a familiar cosmic portrait into a riddle. The sun should push dust and ionized gas outward. Yet here, the plume leans into the light like smoke flowing back into a flame. So, what would it take to make a plume do that? In normal cases, sunlight heats icy patches on the warm side, gas vents outward, and the push of radiation and the solar wind help sweep material into a tail that points away from the sunday. Narrow jets happen when vents are focused or when topography funnels gas into tight streams. Even then, the combined push still favors the anti-sun direction. For a plume to appear sunward, either a directed source must overpower that push locally, or the geometry of what we see is playing tricks with our perspective. Could it all be a camera artifact? That has to be the first question, no matter how exciting the picture looks. Faint structures are often pulled out of noisy data using contrast boosting and edge-finding techniques, and those can amplify specks from background stars or cosmic rays into shapes that mimic real features. The teams involved know this and try to break the result the same way critics would. They check different nights, different instruments, and the raw frames before enhancement. The image still looked internally consistent, which is not proof, but it is a nudge to keep digging. Here is why the stakes feel urgent. 3i Atlas is an interstellar visitor. We do not get to build a custom mission and meet it years from now. It is already on the outbound leg, growing fainter as it climbs away from the sunday. The window to catch decisive data is measured in days and weeks, not decades. That is why a single odd plume matters. If it is a real physical structure, it becomes a handle we can grab with telescopes and instruments to learn what powers it and what the material is made of. Let us lay down the simplest plan of attack. First, we treat the picture like a claim that must survive contact with new data. Independent images at different roll angles should confirm or erase the feature if it is an artifact. Second, we watch for chemistry that correlates with the plume's intensity. If a specific emission line brightens when the plume brightens, that ties geometry to composition. Third, we track timing. If the plume waxes and wanes on a schedule, rotation could be driving a vent in and out of view. All of this only matters if we speak plain truth about uncertainty. No single picture rewrites physics. Patterns do. Reproducible geometry does. Spectra that agree with images do. Timelines that line up across telescopes do. The good news is that the next chapters are already queued up. Multiple observatories on Earth and in space have reported asymmetric features near the same orientation. That does not settle anything by itself, but it raises the bar for the artifact argument and invites a deeper physical model. Here is the promise I can make. We will keep the pace brisk, the language human, and the speculation fenced in by what the data can actually support. When a natural explanation fits, we will say so. When numbers do not cooperate, we will admit it and show you why. And when we reach a fork where evidence could break the tie, we will point you to the measurement to watch, not to a feeling. The sunward plume paradox is either a camera ghost with excellent timing, or the first clean clue that interstellar debris does not play by our local rules. Start with a mental image you can hold. Astronomers dim the blinding heart of 3i Atlas with a circular mask so the camera is not overwhelmed. Around that dark disk, a soft glow blooms. That glow is the coma, a cloud of dust and gas sunlight shook loose from the surface. Nothing controversial there. Then your eye catches a tight filament that threads out from the glow. It is slim, coherent, and when measured against the scale of the image, it spans about 6,000 kilometers in projection. The unsettling part is its direction. It aims toward the sunday. Think of the mask as a pair of sunglasses for the telescope. Without it, the central glare would wash out the delicate structures that matter most. With it, you can finally see the architecture of the coma and any narrow jets that ride through it. Comae often look like fog around a street lamp. Jets look like pencil strokes through that fog. They start near the nucleus and fade into the background as dust and gas thin out. Here the pencil stroke is placed where no one expected to find it. Could geometry be fooling us? That is the fair first test. Telescopes do not draw in 3 dimensions. They project. If a plume leans slightly toward us along our line of sight, it can appear to tilt one way on the sky, even if it points another way in space. You can test that idea by tracking the feature across nights as the viewing angle changes. If projection is the culprit, the apparent angle should drift with simple, predictable steps. Early comparisons show the feature stubbornly holding a similar orientation, which weakens the projection. Excuse, but does not kill it outright. Now, consider the scale. 6,000 kilometers sounds enormous, because it is. Yet in the world of comets, that is a reasonable reach for a focused vent over many hours of steady flow. The surprise is not the length, it is the discipline of the line. Natural plumes wander as the nucleus tumbles, as gas switches on and off, and as solar wind gusts push the finest particles. This line looks like it knows where it wants to go. Timing matters. The raw data were gathered in early August and processed with care, then released in mid-October when teams had enough confidence to show their work. That gap is not a conspiracy, it is the cost of doing this right. Calibrate the detector, remove background stars, check that your enhancement method is not drawing ghost features around trailing starlight, compare stacks taken on different nights. If the line survives that gauntlet, you have earned the right to talk about it out loud. What about the halo around the mask? The coma brightness tells you the object is actively venting. A bright coma with a muted tail can mean large grains that do not travel far, or a dust-to-gas mix that differs from a typical dirty snowball. That context matters because a plume is never just a shape. It is a sign of chemistry and physics underneath. If the plume is real, something is feeding it and holding it together. Place the sun in this picture. Radiation pressure acts like a steady breeze that pushes the smallest dust grains downwind. The solar wind, a stream of charged particles, grabs ions and sweeps them into an ion tail that usually points away from the sun like a taut ribbon. The anti-sun direction is where most comets show their biggest features. In this frame, that region looks quiet while a slender finger stretches toward the light. It is the visual equivalent of smoke flowing back into fire. So what are we actually seeing? At minimum, an internally consistent picture that survives basic checks and aligns with hints from independent observers. At maximum, a physical structure that asks for a new or expanded model of how gas can be injected, collimated, and kept coherent near a star. Between those poles sits the careful middle. A projection effect combined with a narrow vent could sculpt this look. A short-lived burst caught at just the right moment could exaggerate the angle. Both are testable claims. The next frames from other instruments will tell us if this is a one-night wonder or a persistent architecture. If the line reappears when the viewing geometry changes, persistence wins and the artifact story fades. If spectra taken along the line show the same molecules as the surrounding coma, just in different ratios, chemistry joins geometry to confirm a real plume. If the line vanishes when the telescope rotates and the processing method changes, the ghost theory takes the lead. For now, keep the picture in your head. Masked core, bright halo, narrow filament, and an awkward direction that refuses to behave. We are not assigning intent or mystery, we are describing a shape that pokes the rules. That is enough to justify a deeper look and a clear plan to challenge the picture with fresh eyes. When an image shows something outrageous, the first honest move is to try to break it. Astronomy has a century of lessons about pretty ghosts that vanish under better methods. So we start by asking a blunt question. Could processing draw a line where none exists? If the answer is yes, we should find out fast and in public, because a beautiful mistake is still a mistake. Pull back the curtain on how faint structures are revealed. Telescopes collect photons on a detector that is littered with imperfections and noise. You clean the frame with calibrations known as bias, dark and flat corrections. You align multiple exposures so stars line up, then you stack them to boost signal and drown noise. Only after that do you dare nudge contrast and use edge-finding tools to tease out wisps that the eye would otherwise miss. Each nudge carries risk. Push too hard and you turn random speckles into purposeful lines. Background stars are a classic troublemaker. During long exposures, stars trail slightly if tracking is not perfect, or if the target is moving and you align on the comet rather than the sky. Those trails can line up with whatever angle your brain is primed to see, enhance the contrast, and a faint star streak can masquerade as a jet. The fix is simple and brutal. Map the stars in the raw frames, model their trails, and check whether the alleged plume rides exactly where a background streak should sit. If it does, case closed. Cosmic rays are another culprit. High-energy particles spatter the detector with bright, needle-thin hits. They often show up as single-frame spikes that vanish in the next exposure. Stack images without proper rejection, and a spike can sneak through, especially if the stack is small. The defense is multi-frame cleaning with outlier rejection that kills single-frame artifacts. If a line remains across many cleaned frames, cosmic rays lose their alibi. Sharpening can misbehave. Deconvolution methods try to undo blur, introduced by optics and atmosphere, using a mathematical guess of how a point of light spreads. This spread is the point spread function. Get the function slightly wrong or chase low signal regions, and you can generate ringing, faint halos, and spokes that look like spokes in a wheel or lines in a fog. A strong test is to reprocess with a different spread model or with no deconvolution at all and see whether the feature survives. Edge enhancement methods deserve respect and suspicion in equal measure. The common approach looks for places where brightness changes abruptly, then boosts those edges to make wisps pop. It is like turning up the contrast on faint pencil lines. The risk is that noise has edges too. A disciplined team will vary the strength of the filter, rotate the image field, and check the feature against unenhanced stacks. Real structures fade gracefully when you soften the settings but do not flip or relocate. Artifacts tend to warp, slide, or vanish. Detector defects can play tricks. Hot pixels, bad columns, and amplifier glow all stamp repeating patterns that a tired analyst can mistake for structure. The remedy is mechanical. Dither the telescope between exposures so the sky lands on different pixels, then align on the comet before stacking. Real features follow the comet from pixel to pixel. Defects stay bolted to the detector and average away. There is also the geometry trap. A narrow jet that points mostly toward or away from us can project onto the sky at a misleading angle. The antidote is time and rotation. As the Earth turns and as the telescope changes roll angle, projection effects bend predictably. If the alleged sunward line keeps its stance through changing view angles, geometry games lose power. If it swings as basic projection predicts, mystery fades with a quiet click. So what did investigators do here? They checked for background trails by plotting star positions and comparing them to the line. They hunted cosmic ray strikes and verified that the feature persists across stacks with robust outlier rejection. They adjusted the spread model and repeated the processing with softer settings. They examined unenhanced stacks to see if a whisper of the line exists before the algorithms touch it. The outcome is not a victory dance. It is a stubborn remainder. The line weakens when you back off the punches, as it should, but it does not flip, slide, or die. None of this proves the plume is physical. It does something almost as important. It clears the first fence. When a feature survives the boring checks, you earn the right to throw better tests at it. That means new images at different roll angles. Spectra, taken along and across the line, polarization measurements that can tell dust from gas, timing sequences that watch for rhythmic rise and fall. If a camera trick is hiding here, one of those tools will out it. Until then, we hold two thoughts at once. Image processing can absolutely invent structures if you let it run wild. Careful teams can also set traps for their own wishful thinking. In this case, the traps were sprung, and the feature is still on stage. That is not a conclusion. It is an invitation to measure again with fresh eyes and stricter rules. The fastest way to calm an outrageous claim is to ask a simple question. Did anyone else see it? When multiple eyes with different hardware, at different places on Earth, and beyond Earth, report the same odd feature, the center of gravity shifts. You are no longer arguing about a single camera's quirks. You are tracking a pattern the sky itself is insisting on. Start with a clean timeline the mind can hold. In early August, a European 2-meter class telescope in the Canary Islands gathered a sequence that later yielded the sunward filament after careful processing. Around the same season, other teams watching 3i Atlas reported asymmetric brightness in the coma and faint structure that seemed to lean toward roughly the same quadrant. None of those notes felt decisive in isolation. Together they read like a chorus warming up before the performance. Space-based eyes add a different flavor. A major space telescope staring above the blur of the atmosphere logged hints of a narrow structure tucked on the sunward side of the halo. From orbit, you do not fight twinkling air. You get steady, knife-edge resolution and a stable point spread that makes subtle features easier to trust. Even when the feature was faint, the orientation cared about the same compass direction that ground instruments were whispering about. What matters is not poetry but convergence. Instruments with different detectors, optics, and data pipelines begin to echo one another. A Chilean facility catches a skew in the coma flow. A Hawaiian mirror sees a line that refuses the usual anti-sun drift. A European scope tags a filament that prefers the same position, angle night after night when weather and scheduling cooperate. None of those sentences require exotic language. They describe repetition. Repetition is the quiet engine of truth. There is a deeper reason this kind of convergence earns trust. Each setup has its own signature sins. One observatory might be prone to a certain kind of background streak. Another might show mild deconvolution ringing near bright gradients. A space telescope fights none of that, but pays with limited windows and orientation constraints. When a feature shows up across these different failure modes, the shared signal tends to be real while the private ghosts cancel out. Geometry keeps us honest. As Earth turns, and the object moves along its path, the angle between the sun, the comet, and the observer evolves. That changing triangle should nudge any projection effect in predictable ways. Teams mapped the apparent angle through these changes. The numbers wandered within a narrow lane instead of swinging wildly. That behavior does not prove the filament is physical, but it lines up better with a structure anchored to the comet than with a streak tied to background stars or to the instrument frame. Skepticism does not go off duty just because the chorus grows. People can echo one another by habit as well as by measurement. That is why raw frames matter, why sharing calibration files matters, and why a second group repeating the reduction from scratch matters even more. In several cases, independent analysts started from the bottom and worked forward without importing anyone else's masks or filter strengths. Their weaker but persistent filaments landed where the first team said to look. Here is the part that changes the temperature of the room. Journals and preprint servers have begun to carry papers that stop arguing about whether the sunward filament exists, and instead ask what physical processes could make it. That is a cultural pivot. Scientists do not abandon the artifact argument lightly. They set it on the table for later, then reach for models that can be tested with spectra, polarization, and timing. The conversation moves from denial to explanation, so where does that leave us? Not at certainty, not at hype, at a steady, testable claim. Multiple instruments see an asymmetric narrow structure leaning sunward. The angle is stubborn across different nights. Space-based and ground-based data rhyme. The right response is to deepen the cross-checks and widen the toolset. That means spectra taken along the filament, polarimetric maps that separate gas from dust, and time series that test whether rotation modulates the signal. When many eyes point to the same thin line on the sky, you do not declare victory. You sharpen the next question. If this is a real plume, what is in it? How is it being focused? And why does it lean into the light? If it is still a ghost we have not trapped, which specific test will finally make it vanish? That is the hunt we are on together. If you have ever watched sawdust blow off a workbench when a fan is running, you already understand the basic rule for comet tails. The sun is the fan. A comet is the workbench. Dust and gas are the sawdust. Turn on the heat, material lifts, and the steady push drives it downwind. That is why almost every textbook image shows tails stretching away from the sunday. It is not artistic habit. It is physics that behaves the same way every single day. Start with the engine. Sunlight warms exposed patches on a comet's surface. Ices buried in the crust sublimate into gas. That gas rushes out through cracks and vents. The surface recoils the tiniest bit in the opposite direction, a pocket-sized rocket effect, while the new gas carries dust grains along for the ride. At this moment, everything still looks local, but space is not still air. Two large-scale pushes take over, radiation pressure and the solar wind, and both prefer the anti-sun direction. Radiation pressure is simple to feel, even if you cannot see it. Photons from the sun carry momentum. When they hit a dust grain, they give it a tiny shove. One shove is nothing. Trillions matter. The smaller and lighter the grain, the bigger the effect. Over hours and days, those shoves herd dust downwind and stretch the dust tail. That is why the finest dust peels off first and curves gently along the comet's path like smoke drifting with a breeze. The solar wind is different. It is not light. It is a river of charged particles streaming out of the sun at hundreds of kilometers per second. Gas molecules that lose electrons become ions. The wind grabs these ions with magnetic fields and drags them straight away from the sunday. That creates the ion tail, a narrow bluish ribbon that often points almost exactly anti-sun because magnetic lines are ruthless about direction. If the dust tail is a painter's brushstroke, the ion tail is a laser pointer. Dust and gas do not behave identically. Dust grains are heavy enough to keep some memory of the comet's orbital motion, so their tail curves. Ions forget quickly and snap into the wind's flow lines. Meanwhile, neutral gas in the inner coma swirls and collides, making a round halo around the nucleus. This three-part picture, round coma, curved dust tail, straight ion tail, is the normal family portrait of an active comet. A sunward pencil line does not belong in that portrait unless something unusual is happening. Could the nucleus itself shape a narrow jet? Yes. If a vent is small and the local terrain funnels gas like a nozzle, you can get a focused jet that launches material as a tight column. As the nucleus rotates, that column sweeps like a lighthouse beam and can carve fans or spirals in the inner coma. Even so, the column is quickly bent downwind. Think of a hose spraying into a gust. The water exits straight, then the breeze takes command. Projection can also play tricks. We see a three-dimensional dance projected onto a flat sky. A jet that points mostly toward us can appear to tilt at a surprising angle on the image plane. But projection has a tell. As the viewing geometry changes, the apparent angle should drift in predictable ways. When a line clings to the same sunward quadrant across changing nights, projection alone grows less convincing. So what force could fight the push? There are natural possibilities that still respect the rules. Heavy grains launched fast can coast a short way before the breeze bends them. A vent aligned just right on a rotating body can momentarily point near the sun line before sweeping away. Gas that is more collated than dust because molecules can stream, while dust stumbles could sketch a slender feature that looks wrong at first glance, but still yields to the wind farther out. Each of these effects has a signature. Each can be checked with spectra, polarization, and timed imaging. The bottom line is not mystical. The sky is windy near a star, photons shove, plasma drags. Most of the time, those pushes dominate quickly, which is why comets wear their tails like capes that trail behind them as they run. When you see a plume that seems to run into the wind, you do not rewrite physics on sight. You ask what could briefly overpower or outsmart the breeze, or how the camera's flat view might be stacking the deck. Then you measure. If the feature stands up to those tests, you go back to the rulebook and add a page. Light carries fingerprints. When sunlight excites atoms in a comet's coma, those atoms glow at very specific colors. Spread that glow into a rainbow and you get a barcode written by nature. For 3i Atlas, the barcode spells something awkward. Nickel shouts, iron whispers, or stays silent, depending on distance from the sunday. That is backward from what most astronomers expect. In space, and in rocks from our solar system, iron is usually the louder cousin. Here, nickel steps forward first. Let us make that concrete without math. Observers pointed high-resolution spectrographs at the coma across several nights. They saw bright lines where neutral nickel atoms advertised themselves. In the same regions, the iron lines were faint or missing. Later, closer to the sun by a clean step in distance, iron finally appeared. The balance between the two metals did not just drift. It flipped past a threshold that behaves like a thermal switch. Why is this so strange? In ordinary comets, metals enter the gas phase when dust grains are heated or shattered. Iron and nickel often travel together because they are locked in the same mineral grains. If you free one, you usually free the other in roughly the same proportion you find in meteorites and cosmic dust. It is not a perfect rule. It is a sturdy habit. 3i Atlas breaks the habit with confidence. Nickel leads, iron lags until the object moves inward to a warmer zone. There is a natural family of ideas that can mimic this behavior. One involves metal carbonyl compounds, where a metal atom bonds with carbon monoxide molecules. Some nickel carbonyls are volatile at surprisingly low temperatures. Iron has its own carbonyls, but their stability and release temperatures differ. If the nucleus formed in a carbon-rich oxygen-limited environment, nickel carbonyl might survive in pockets that begin to vent earlier than iron compounds. As heat increases, the iron-bearing species wake up, and iron lines join the spectrum. That is a tidy story. Reality will try to mess it up. Another route uses structure rather than chemistry. Imagine a nucleus with layers. The outer skin holds nickel-rich grains that are easier to liberate. The deeper layers trap iron in stronger minerals or larger particles that do not gas off until the temperature crosses a higher mark. As the object moves inward, the thermostat clicks, and iron finally joins the party. Layering is common in small bodies that have been processed by heat and stress. The question is whether layering can be sharp enough to make the on-off look we see. There are tests that do not require hand-waving. If carbonyl chemistry is in play, carbon monoxide should be abundant where nickel lines are strongest. If layering drives the switch, dust particle sizes and mineral fingerprints in the infrared should change at the same distances where the metal balance flips. If nickel really dominates the gas while iron hides in the dust, Polarization maps can help separate their contributions by showing how light scatters off different grain sizes. The nickel first pattern also speaks to the broader mystery. A plume that leans sunward needs motive power and a way to stay narrow. If the gas feeding that plume carries an unusual metal signature, the chemistry and the geometry are friends rather than strangers. A vent that coughs out nickel-bearing species before iron might reflect a local pocket of material with different binding energy, or a microstructure that acts like a nozzle. That does not imply anything artificial. It does imply an origin story or thermal history that is not common in our local comet zoo. Here is where cautious excitement is justified. Metal lines are hard to fake. You can invent a streak with careless image processing, but you cannot conjure a nickel emission line unless nickel atoms are truly there, fluorescing in sunlight. When independent teams report the same lines with similar timing and distance thresholds, you gain confidence that the anomaly is physical, not procedural. The next step is to tie the metal balance to other molecules. If regions with stronger nickel also show specific carbon-bearing species in distinct ratios, the chemical mechanism tightens into focus. We should also be brutally clear about what would weaken the case. If improved iron detections creep outward to the same distances where nickel first appeared, that would point to sensitivity limits rather than exotic release. If the nickel signal turns out to ride on top of a background we misread, the pattern softens. That is why the most valuable measurements now are not single spectra, but sequences that track the metal lines as a function of time and distance while other instruments map dust behavior. For now, the clean reading is simple. 3i Atlas speaks in nickel before iron until it crosses a warmer line in space. That odd cadence is either a fingerprint of uncommon chemistry in a foreign nursery, or a sign that structure and temperature are playing a very specific duet inside the nucleus. In either case, the metal puzzle is not a side story. It is a clue that sits right next to the sunward plume and asks the same question in a different dialect. What on this object turns on early? What waits? And why? Most comets behave like dirty snowballs. Water ice wakes first as sunlight climbs, then carbon monoxide and carbon dioxide add their voices as the nucleus warms. 3i Atlas flips that melody. Infrared spectra show carbon dioxide running the show while water stays strangely muted. The numbers are not the point here. The shape of the story is. Carbon dioxide is winning by a wide margin where water should be the natural leader. Why does that matter? Water is the easiest volatile to wake at the distances where most comets begin to glow. It takes less heat than many other ices to begin lifting off the surface. When water goes first, its gas flow becomes the conveyor belt that carries dust away and helps shape tails. If water stays quiet while carbon dioxide roars, the conveyor belt runs on a different fuel. That changes the density of the gas, the way dust grains couple to the flow, and even how narrow vents collimate plumes. There are two families of explanations that fit without magic. The first is birthplace. 3i Atlas may have grown in an environment richer in carbon-bearing ices than our local nursery. Think of a star-forming region where carbon monoxide and carbon dioxide were abundant and easily trapped in grains. In that case, the nucleus would carry pockets where carbon dioxide sits near the surface while water is buried or depleted. Even modest heating could then drive carbon dioxide outgassing long before water gains traction. The second family is thermal history. An object that spent ages in deep cold can trap volatiles in layers that respond to heat in stages. A thin crust forms over time. Sublimation vents chew narrow paths upward. If carbon dioxide is closer to those paths, it escapes first and builds an atmosphere around the nucleus that is chemically skewed. Water may still be present in bulk, but it is trapped in deeper reservoirs that only open when the heat budget crosses a higher threshold. Both ideas make predictions we can test. If birthplace sets the chemistry, we should see a consistent pattern across multiple molecules linked to carbon-rich environments. Ratios among carbon monoxide, carbon dioxide, and simple hydrocarbons should track together as distance from the sun changes. If thermal history dominates, we should catch step functions rather than smooth ramps. A quiet plateau, followed by a sudden rise when a seal breaks or a deeper seam is exposed. Gas composition also shapes the geometry we see. Carbon dioxide gas is heavier than water vapor, yet can carry energy efficiently when it streams through a tight vent. If a plume is fed by carbon dioxide-rich gas from a focused opening, the flow can remain coherent over long distances before radiation pressure and the solar wind peel the dust away. That would help a narrow filament survive in a direction that seems counterintuitive, at least near the nucleus, where the flow is densest and fastest. There is another wrinkle. Dust rides differently in different gases. Water vapor tends to entrain a wide size range of grains. Carbon dioxide can favor specific sizes depending on the throat of the vent. and the local pressure. If the gas prefers larger grains early on, the tail can look muted even while the coma is bright. Large grains do not race far from the source before gravity, and drag slow them. The result is a bulky halo with less dramatic tail structure, exactly the kind of portrait that first raised eyebrows for 3i Atlas. None of this requires speculation beyond nature. It does demand careful mapping. Spatially resolved spectra along the suspected plume can tell us whether carbon dioxide is enhanced inside the filament compared with the surrounding coma. Time series across several nights can reveal whether waterlines wake up as the object crosses inward through specific heat zones. Polarization maps can separate the behavior of large dust grains from fine particles, testing whether the gas flow is picking favorites. There are ways this could fail. If deeper observations show waterlines stronger than first reported once sensitivity improves, the apparent dominance of carbon dioxide may shrink into an instrumental limit. If carbon monoxide and other carbon-bearing species do not behave in step with carbon dioxide, then simple origin stories become less convincing. That is why the next round must include coordinated campaigns across infrared, optical, and ultraviolet, with the same regions of the coma sampled in the same time windows. For now, the clean read is striking. 3i Atlas is running on carbon dioxide while water waits its turn. That single twist explains a surprising amount of the weirdness. It changes how jets launch, how dust lifts, how tails form, and how a narrow structure could stay focused near the sunline before the sky's steady push takes over. The chemistry is not a footnote to the geometry. It is the engine under the hood, and it is not tuned the way we are used to hearing. Every living system pulses, hearts beat, volcanoes breathe, even geysers keep a rhythm when their chambers fill and empty. Now, the light from 3i Atlas appears to rise and fall on a steady cadence near 4 hours, with hints of a second drum at 2. That is not a stray flicker. It feels like a metronome hiding inside a chunk of ice and dust drifting through sunlight. Start with the simplest picture. If the nucleus spins once every 4 hours, active patches rotate in and out of daylight like windows on a turning carousel. When a vent faces the sun, it warms, pressure rises, and gas flows hard. As it rotates away, the patch cools and the flow softens. To an observer, brightness climbs and falls with a tempo set by the spin. Many comets do this. It is a comfortable thought because it ties the rhythm to a basic property you can imagine holding in your hand and spinning, but the data carry some neat edges that make the comfort wobble. The 4-hour signal looks clean rather than messy. Real surfaces are lumpy, vents sputter, dust clogs throats. If chaos ruled, the rhythm would drift like a drummer, losing the beat in a loud room. Instead, the pulse keeps time over many cycles. That does not break physics. It does hint at an active region that is surprisingly stable, or a geometry where a single vent dominates, and the rest of the surface plays along quietly in the background. Here is another natural route. 2 pieces instead of 1. A contact binary looks like a snowman pressed together. A separated binary is 2 lobes, orbiting each other at close range. Tides flex the pair. Heating and shadowing change with each orbit. A 4-hour period could be the time it takes for the pair to swing around, driving a repeating pattern in gas production. We have seen small bodies like this before. The trick is that a binary often leaves fingerprints in the light curve shape. Subtle humps, unequal peaks. Analysts will hunt for those shapes in the time series. Could we be fooling ourselves with sampling? Telescopes observe in chunks, not continuously. Weather, daylight, and schedules carve holes in the record. If you sample unevenly, noise can conspire to mimic a period near a convenient round number. Astronomers know this and beat on the data with tools that test whether the period survives when you reshuffle observation times or when different teams analyze different nights. The 4-hour beat has held up under those stress tests more often than not, which keeps it on the table as a real property rather than a statistical accident. Now, bring the plume back into the room. If a narrow vent is responsible for the sunward filament, rotation could swing that nozzle into and out of its best alignment with the sunline. The plume would brighten at a specific phase, then soften at another, writing a bright dark pattern that matches the spin. That gives us an immediate, testable map. Take a time series of images over a full cycle and track whether the filament waxes and wanes on schedule. At the same time, collect spectra to see whether specific molecules strengthen in step. If chemistry surges when the line sharpens, the geometry and the gas are dancing to the same drummer. There is one more path that tempts the mind: a slow fill and release. Imagine a pocket under the surface connected to space through a narrow crack. Gas builds pressure until a threshold is reached, then surges through the throat. Pressure drops, The pocket refills, and the cycle repeats. On Earth, geysers run on this kind of feedback. In a comet, that is harder to maintain because porous rubble does not hold tidy chambers. Still, if the crust is sintered by repeated heating or by mineral cements, you could stabilize a valve-like behavior long enough to write a rhythm into the light. Why does the neatness of the beat matter? Because a clean clock makes prediction possible. If rotation leads the dance, the phase of peak brightness should remain coherent for weeks, drifting only as viewing geometry changes. If fill and vent feedback drives it, the timing might wander with solar input or with changes in the vent throat as grains erode. If a binary is involved, secondary wiggles may appear at harmonics that betray the orbital motion. Each case sketches a different future. The data decide which sketch matches the sky. There are ways this could all go soft. If the 2-hour hint grows while the 4-hour fades, the original period may have been a harmonic, born of sparse sampling. If the phase drifts randomly from night to night, rotation loses its grip on the explanation. If different molecules peak at different times with no consistent relationship to the light curve, then the pulse is not tied to a single engine, but to overlapping processes that happen to share a loose timescale. For now, the clean statement is short enough to hold. 3i Atlas ticks near 4 hours, and that tick may be the key that links shape, chemistry, and the strange geometry of the plume. A clock is a gift. It lets us fold data from many nights into one coherent picture and test ideas with the sharp edge of prediction. If this object keeps the beat as it moves outward, the rhythm will either lock the case for rotation-driven venting or force us to admit that something more organized is hiding under a skin of ice and dust. Let us give nature the steering wheel and see how far it can drive before we reach a cliff. The sunward filament could still be a stack of ordinary effects that only looks extraordinary when they line up just so. If we can explain the picture with familiar physics, we should. If the explanation needs too many coins to land heads at once, the odds will start to argue with us. Begin with layered ices. A small body can build a crust over time. Heat from sunlight bakes the surface, sinters grains, and seals shallow pores. Beneath that crust sit pockets where different ices wait their turn. Carbon dioxide can lie closer to the surface than water in some regions. When the sun warms those spots, gas finds narrow cracks and sprints outward before water wakes up. That flow can carve a tight jet. Early in the day, the jet looks sharper. Later, it softens as other patches join the outgassing chorus, and turbulence spreads the flow. Add local terrain. A vent that opens inside a pit or along a ridge can act like a nozzle. Gas streaming through a tapered throat stays aligned for a while, just as water stays straight for a meter before a cross breeze bends it. If that throat happens to face near the sunline during part of a rotation, you could freeze a frame and find a plume apparently leaning toward the light, even though the wind bends it a little farther out. A thin line near the nucleus would be consistent with this near-field discipline, while the far field obeys the push. Now bring in rotation. A 4-hour spin turns a nozzle through a full circle with neat regularity. During a short slice of that circle, the vent points close to the sunline. During the rest, it points elsewhere, and any plume fades into the general glow. Stack many exposures aligned on the comet, and you end up imprinting the preferred direction where the vent spends the most time near its best alignment. The result is a faint but persistent filament that survives stacking while sharper transient directions average away. There is also the two-body path. A contact binary can shape gas flow in ways a single lump cannot. If two lobes touch, the neck between them collects shadow and cold. Volatiles can remain there longer and then vent into a confined space. When that gas escapes, it can form a focused sheet or narrow ribbon that prefers one direction set by the local geometry. If the pair rotates with a tidy period, the plume may repeat its stance night after night. A separated binary can do something similar, through tidal flexing and repeating stress patterns that open and close cracks. Chemistry can help nature cheat. Nickel-bearing molecules that free themselves at lower temperatures than iron will seed the gas early. If those species flow through the dominant vent, they can change the density and cooling behavior of the jet. A denser or cooler gas can carry dust differently and maintain collimation a little longer before the solar wind and radiation pressure reshape it. That would tie the strange metal balance to the surprising geometry without calling in any exotic actors. Projection still deserves a hearing. Telescopes turn a three-dimensional dance into a flat drawing. A jet that points mostly along our line of sight can project into a sky angle that looks suspiciously sunward. The test is time. As the viewing geometry changes over days, projection should make the apparent direction slide in a predictable way. If it does, natural projection gets a win. If the angle clings to the same lane through changing geometry, projection starts to lose its alibi. Here is the honest rub. Each of these ideas is possible. Layered ices exist. Vents act like nozzles. Rotations fold activity into repeating patterns. Binaries are common among small bodies. Projection tricks observers all the time. The question is not whether any one of them can help. The question is, how many have to stack perfectly to recreate exactly what we see? When you need too many lucky breaks, the probability shrinks. When a single clean mechanism can predict multiple features at once, the probability grows, so we write down predictions that separate the crowd. If a nozzle plus rotation drives the plume, the filament should brighten at the same phase each cycle, and its inner angle should match the surface orientation implied by the spin. If layering controls which gas leads, metal lines, and carbon-bearing molecules should rise and fall together at specific distances from the sunday. If a binary is responsible, the light curve should show telltale asymmetries, and the phase of the plume should track the orbital beat. There are also decisive negatives. If the filament flips or vanishes when the telescope rotates, or when a different processing pipeline is used, the artifact takes the lead. If the apparent direction slides exactly as simple projection predicts, we retire the idea of a physical jet leaning into the wind. If spectra along the line show no difference from nearby coma, geometry wins and chemistry steps back. This is how we keep our balance. We let nature present its best portfolio of familiar tricks, and we measure without fear or favour. If the ordinary can carry the load, we should applaud. If the ordinary needs too many crutches, we admit it and look for a cleaner engine. Either way, the next observations will pay for or cancel these ideas in daylight, and the story will be stronger for the test. Here is where the story tiptoes to the edge of the map. What if a small part of 3I Atlas is not just rock and ice? What if a nickel-rich component is embedded in an otherwise natural nucleus and is now shedding telltale material as it weathers? That idea sounds wild. It also makes specific predictions that nature alone must work hard to imitate. We can explore the thought without losing our grip on evidence. Start with why nickel matters. Engineers love nickel alloys for ugly environments. They shrug at heat, they resist corrosion, they hold strength in conditions that make ordinary metals sulk. If you wanted a structure to ride interstellar space for ages, a nickel-heavy skin would be a rational choice. Over time, in a harsh vacuum bathed in radiation, surface layers can pit, crack, and slowly ablate. If that skin were exposed inside a cometary crust, warming near the sun could release nickel atoms and simple carbon-bearing fragments into the coma long before iron-rich minerals let go. Now, connect that to the plume. A directional opening is the simplest way to force a jet to pick a side. A nozzle does not care which way radiation pressure prefers to push dust later. Gas leaving a throat can be collimated for many core diameters before the environment sculpts it. If a nickel-rich piece had seams or vents that happened to face near the sun line during part of a rotation, you would get a focused filament that points the wrong way for a short inner distance, then yields to the wind farther out. The near field would look disobedient. The far field would rejoin the rules, layer in the metals puzzle. Nickel lines stand tall early, iron hides until the object crosses a warmer boundary. An engineered skin with little iron would feed exactly that bias. As deeper layers heat, iron begins to appear, and the balance shifts. The chemical switch we see with distance would then reflect a physical transition from a processed surface to more natural interior material. The 4-hour heartbeat could be the rotation of a body that repeatedly swings a vent into its strongest stance, carving a metronome into the light curve. This idea demands the highest bar. Extraordinary claims need extraordinary proof. That proof is not a dramatic image or a single odd ratio. It is a pile of independent signatures that line up so cleanly that the mundane collapses. What would that pile look like? Spatially resolved spectra that show nickel and related molecules enhanced along the filament compared to the surrounding coma. Polarization patterns that separate gas-dominated flow inside the filament from dust-dominated haze outside it. A stable phase relation between the plume's brightness and the rotation period across many nights. A thermal map that reveals a small patch with unusual heat behavior compared to its neighbors. There are also nails that would shut the door. If higher sensitivity spectra show iron present in lockstep with nickel, at the same distances where nickel first appears, the engineered bias weakens. If the plume's chemistry matches the general coma with no enhancement along the line, a directional vent still stands, but the alloy story does not. If the filament angle wanders exactly as projection predicts when geometry changes, a physical nozzle is no longer required. And of course, if different teams, using different pipelines, cannot reproduce the feature, the whole thought experiment goes back into the drawer. Why keep this possibility on the table at all? Because speculation can be disciplined and useful when it writes checks that data can cash. The engineered alloy thought gives us a shopping list. Look for isotopic ratios that do not match natural cosmic averages. Hunt for simple industrial byproducts that lack easy natural pathways in a cometary crust. Search for edges that are too straight, temperature responses that are too sharp, and timing that is too tidy for a rubble pile. If none of that appears, the idea dissolves, and we learn which tests actually mattered. If some of it does appear, we still do not leap. We would then ask whether there exists any natural environment that could imprint the same signatures on primordial material, a carbon-rich nursery with odd metallic chemistry, a history of shock processing that fractionated metals, an ancient surface that sintered into a pseudo-alloy through slow radiation cooking. Nature is creative and should get first credit for creativity. The value of this thought is not in its romance, it is in its discipline. It draws a bright line between what would merely be weird and what would be unmistakable. Until such evidence exists, the safe place to stand is on the natural side of the river, with a bridge blueprint in hand. If the river narrows and the pillars appear, we will know when to cross. The fastest way to earn truth is to invite defeat and see what survives. So let us write tests in plain language that could knock our favourite ideas flat. If the sunward filament is a ghost, a trick of processing, or a projection sleight of hand, there are clean ways for the sky to tell us so. If it is real, the same tests will make it harder to deny with every new night. Start with rotation and timing. If a single vent is carving the filament, its brightness should rise and fall in step with the 4-hour beat we have been tracking. That prediction is specific. Phase the images by the beat and stack them in bins. The filament should sharpen in one bin and soften in the opposite bin. If the pattern refuses to lock to any phase for weeks, the rotation story loses power. If the phase holds like a drumline, rotation wins the first round. Now, test geometry. Projection tricks change with viewpoint. As Earth moves and the roll angle of a telescope changes, a fake sunward tilt should slide in a predictable way. Plan a campaign where different observatories take turns across many longitudes, so the feature is chased through a full set of angles. If the line swings as the simplest geometry demands, we downgrade the claim. If it clings to the same sunward lane through the changes, geometry has less room to hide. Processing next. The surest antidote to pipeline bias is diversity. Run the data through multiple reductions with different point spread models, different edge treatments, and different choices for background removal. A real filament should fade gracefully as you soften the settings, but it should not flip sides or wander away from its lane. An artifact will often warp when you change the math. If 3 teams with 3 pipelines report the same position and extent, the ghost theory weakens. Chemistry is a powerful referee. Take spectra along the suspected filament and just off to the side. If the filament is an illusion, the mix of molecules should match the surrounding coma within uncertainties. If the filament is a physical flow channel, some ratios should shift inside it. Carbon dioxide lines might sharpen inside the line, nickel might brighten by a steady factor, water might lag. The exact direction of change is less important than the consistency of a difference that maps the filament's path. Polarization helps separate actors. Dust and gas scatter light differently. Map the inner coma with a polarimeter and look for a ribbon of values that traces the filament in. Images. If the map is flat and featureless where the filament should be, we are likely staring at noise sculpted by processing. If a crisp stripe appears, the physics gains a second witness that does not care about contrast tricks. Space plasma is a quiet judge. When the ion tail crosses a spacecraft, particle detectors can weigh ions by mass to charge and record their mix. If observations on the ground talk about unusual metals or a skew toward carbon dioxide while the in situ sample looks textbook normal, the burden shifts back toward misinterpretation. If the spacecraft sniffs the same odd mix we claim from afar, 2 very different instruments are telling one story. Mars orbiters offer a geometric trump card. A camera near Mars sees the comet from a different angle than we do. If those images appear, and they show a slim structure tucked sunward from that vantage too, projection excuses will run out of road. If they show a symmetric inner coma with no narrow feature at all, then we must ask whether our processing sharpened nothing into something. There are negative outcomes worth celebrating. If independent teams erase the filament when they correct for background star trails, we should accept that and move on. If iron turns out to have been hiding under the floor of our sensitivity from the start, the nickel first claim becomes less exotic and the chemistry returns to a cooler story. If the 4-hour beat dissolves under better sampling, rotation becomes less relevant and we will look elsewhere for order. The point is not to win an argument. It is to make predictions that are so clear they embarrass us if they fail. We have them in hand, a phase-locked plume or not, a geometry that holds or slides, a chemical ribbon or a flat field, a polarized stripe or a blank, a spacecraft reading that matches or contradicts the ground. Over the next observing windows, these tests will either prune the story to something ordinary or harden it into a result that earns a fresh page in the book. Either outcome is progress. Either way, the sky gets the final word. Sometimes the universe throws us a bone. We did not launch missions to chase 3I Atlas. Yet 2 spacecraft happen to be in the neighborhood with instruments that can taste the coma and feel the wind of its ions as they pass. The distances are big by human standards and small by cosmic ones. We will not get movie close-ups. We can still get answers that only space can give. Think of the toolkit they carry. Cameras that can map the broad glow and any large-scale asymmetry without the blur of Earth's atmosphere. Spectrometers that split light into the fingerprints of molecules and atoms, including metals if the signal is strong enough. Particle detectors that weigh ions by how they fly through electric and magnetic fields, telling water ions from carbon dioxide ions and separating both from heavier species. Magnetometers that read the bend and twist of the interplanetary magnetic field as it drapes around an active coma. None of these tools care about image processing tricks. They measure what is actually there. Start with the spectrometers. From millions of kilometers, they can still sample light that has crossed the coma like a probe beam. If carbon dioxide truly dominates while water lags, that balance should show up as clean lines at the right wavelengths. If nickel is present in unusual abundance, its lines can spike above the noise when the geometry cooperates. The key is patience. Spacecraft do not swivel like handheld cameras. Pointing takes planning and fuel. When a window opens, teams will time their looks to catch the comet against a dark background and avoid glare from the sunday. Now, picture the particle detectors waiting like cupped hands. As the ion tail sweeps past, those detectors will count and sort the charged pieces of the coma that the solar wind has grabbed. A normal comet writes a familiar recipe. Water group ions lead the mix. Carbon monoxide and carbon dioxide leave clear signatures. If this object is really different, that recipe will tilt. More carbon dioxide ions than expected. A trace of metal ions at levels high enough to notice. Even the speed distribution can speak, revealing whether ions were picked up gently or ripped away in a surge. Magnetometers add a map you cannot draw from Earth. As the wind flows around an active coma, magnetic field lines bend like streamers around a rock in a river. The shape and strength of that draping depend on how much gas is being ionized and how conductive the environment becomes. If the sunward plume is real and carries gas that ionizes efficiently, the draping pattern can become lopsided, a subtle fingerprint of directional outflow written directly into the field. If the field stays vanilla, the case for a strong, focused flow weakens. The cameras still matter, even from afar. They will not resolve the nucleus or reveal tiny vents, but they can trace the broad outline of the coma and tail without the atmospheric distortions that haunt ground images. A persistent asymmetry in the same quadrant where the filament appears from Earth would be a quiet confirmation from a very different vantage. A smooth, symmetric glow would tug the story back toward artifact or projection. It is important to be honest about limits. These missions have primary goals that do not involve this visitor. Every degree of pointing burns fuel that is needed later. Observation windows are constrained by power, thermal limits, and communication schedules. The comet will be faint against a bright solar background. There will be times when geometry simply refuses to cooperate. A non-detection does not equal a refutation unless the conditions were right to see what we claimed. So we set predictions that respect those limits. If the particle instruments sample the tail, the ion mix should lean heavily toward carbon dioxide if the ground-based spectra are right. If nickel is genuinely abundant in the gas, a faint population of heavy ions should register above background. If the magnetometers slice through a region bathed by a focused outflow, draping should skew in a way that lines up with the suspected plume direction. If none of these patterns appear under good conditions, we lower our confidence in the exotic chemistry and the directional jet. There is a deeper reason to get excited about these passes, even if the signals are subtle. They tie the geometry we draw from images to the physics the plasma feels. They give us a language to connect pictures and particles, to link a narrow line on a photograph to a bend in a magnetic field measured far away. That is the kind of cross-check that settles arguments in science. It is also the kind of result the audience can trust, because 2 very different senses are reporting the same thing. The clock is ticking. Over the next days and weeks, those instruments will take their shots. If they see a skewed field, a tilted ion recipe, and a carbon dioxide heavy mix, the path forward sharpens. If they do not, the debate narrows too. Either way we learn. Either way the mystery shrinks in the right direction, toward an answer the sky will accept. The comet brushed past Mars earlier this month, close enough that cameras in Martian orbit might have caught a clean side angle of the inner coma. That is the kind of bonus shot storytellers dream about. Fresh geometry, a second vantage, a chance to see whether a narrow feature really hugs the sunward side or whether our Earth view is playing tricks. Yet public images from those orbiters have been slow or absent. Silence invites speculation. We can do better than speculation. We can explain why silence often happens and what the first frames, whenever they appear, will actually mean. Start with priorities. Mars orbiters are at Mars to study Mars. Their time is booked months ahead to watch dust storms, map mineral seams, or monitor seasonal frost. Slewing a spacecraft to chase a fast-moving target is not free. It costs planning, fuel, and sometimes the loss of regular science. Mission teams weigh those costs against the chance of a useful comet image and sometimes decide to take the shot only if it fits without trampling primary goals. That is not secrecy. That is stewardship. Next is the pipeline. Raw frames from deep space do not leap straight to the internet. They run a gauntlet of calibration. Dark current is subtracted. Hot pixels are flagged. Optical ghosts and stray light are modeled. Star fields are cross-checked so pointing is nailed down. Teams compare repeated exposures and strip out cosmic ray hits. Only then do analysts assemble the best stacks and write the captions that tell a global audience what they are looking at. That work takes time, especially when the target is faint and the background is bright. Geometry also matters. From Mars, the comet sits at a different phase angle than from Earth. The Sun, the comet, and the camera form a new triangle. That can be wonderful, or it can be unhelpful. If the sunward side falls into glare, a narrow feature could drown in scattered light. If the camera cannot roll to place the sun where the instrument tolerances demand, engineers will refuse the shot rather than risk the hardware. None of that maps to mystery. It maps to constraints. Still, the curiosity is fair. If images exist, and if they are good enough, what would they tell us? A clean detection of a slim structure tucked toward the sun from that vantage would slash the projection argument to ribbons. A symmetric inner coma with no line at all would push hard the other way. A lopsided halo without a knife-edge plume would land in the middle and force us to ask whether our processing on Earth sharpened a soft gradient into a filament. Each result narrows the field. Each is worth waiting for. There is also the human factor. Teams are cautious when a picture could ignite headlines. They want to be sure their processing is not. Painting a story onto noise. They run the reduction twice, then again with a different mask. They ask colleagues in other countries to try a blind reduction. That is not foot-dragging. It is how you avoid a public correction that sours trust. The fastest way to lose an audience is to post a dramatic frame and retract it a week later. The slower way wins in the long run. Let us keep expectations honest. A Mars orbiter is not a magic microscope. Even the sharpest camera will not resolve vents or carve the nucleus into a clear shape at these distances. What it can do is draw the outline of the inner coma under a different sun angle and check whether a preferred direction persists when Earth is not the observer. It can also set upper limits. If no narrow feature is seen above a certain brightness, we learn how faint the filament must be if it exists, which feeds back into models of gas flow and dust loading. There is a cautionary scenario too. Suppose an image appears and shows a tease of asymmetry that supporters read as a plume and skeptics read as ordinary structure. In that case, the most valuable thing would be coordinated ground observations taken within hours, so the two views can be compared directly. Without that coordination, the debate will lean on taste rather than physics. The fix is simple. When a window is announced, telescopes on Earth should plan to watch at the same time in the same filters. So yes, the quiet is frustrating. It is also normal. If and when those images arrive, they will not end the story by themselves. They will take one clean bite out of the uncertainty. Either the sunward preference shows up from Mars, which would be a strong vote for a real persistent feature, or it does not, which would make projection and processing climb back up the leaderboard. In both outcomes, the investigation tightens. That is the only victory that matters. Coincidence is the universe's favorite magic trick. In the same stretch of days when 3i Atlas looked most peculiar, several small bodies dove into the sun, and a bright point near the moon in a rocket launch video set comments sections on fire. It is tempting to weave a single plot from those threads. Could the sun grazers be fragments? Could the bright point be a companion? Or are we stitching a story out of unrelated sparks because our brains hate loose ends? Start with sun grazers. Solar observatories catalogue these doomed visitors all the time. Families of fragments fall along similar paths like debris from an ancient breakup, and there are seasons when several arrive in quick succession. Base rate thinking matters here. If an instrument that watches the sun every day expects a handful of small comets to perish each month, then 4 in a week is not an omen. It is weather. The sensible move is to ask whether their directions and speeds truly align with 3i Atlas, or simply share the same general quadrant, because that is where we aim our attention. Testing a connection demands data we can touch. Spectra would help, but sun grazers near the sun are fast, faint, and swallowed by glare. Most detections are made with coronagraphs that block the sun and reveal a thin ring of space around it. Those instruments produce clean images of motion but little chemical detail. Without composition, we lean on dynamics. If the sun grazers were fragments, their orbits would line up with 3i Atlas in a way geometry can explain. If they do not, the case for kinship fades. Now the bright point near the moon. Cameras aimed at a glaring disk are prone to tricks. Internal reflections can bounce light around the optical path and paint ghost dots that hover or drift. Sensors can create blooming when a bright target overfills wells and spills charge into neighbours. Lenses with multiple elements can draw tiny echoes of the main light source in unexpected places. A convincing check is to compare different cameras and angles. If the point appears in one setup and not another under the same sky, the odds tilt toward artifact. If multiple independent systems record the same point in the same place, interest rises, and we go hunting for a tracked object that fits. Even when the bright point is real, ordinary explanations often win. A slow-moving satellite catching sunlight near the limb, a distant high-orbit vehicle flaring for a moment, a piece of upper-stage hardware on a weird path. We have access to catalogues that track many, but not all, objects in Earth orbit. A careful analyst will test those catalogues first. Only when the point refuses to match known paths do we move to the next rung and ask for simultaneous observations from distant locations that can triangulate a distance. Here is a useful mindset. Pattern seeking is a survival skill, not a truth machine. Our ancestors gained more from seeing the hint of a predator in the grass than from missing it. Today, that instinct makes us link events that merely rhymed in time. The antidote is comparison. How often do sun grazers cluster? How often do bright points appear near the moon in video gear pushed to its limits? When you set 3i Atlas in that wider statistical frame, the specialness often softens. But do not swing to cynicism. If there is a link, it will leave footprints. A timing relation between the heartbeat of 3i Atlas and the arrival of small objects on solar approach would raise eyebrows. Shared directional cues that hold across geometry would do the same. A bright point that reappears at predicted times and positions, with a spectrum that matches the comet's odd chemistry, would turn whispers into a plan. These are high bars. They're also clear bars. That is healthy. For viewers following along at home, here is the practical way to hold this. Keep curiosity alive and your standards higher. Enjoy the weird video clips. Then ask for a second camera, a second location, a second instrument. Enjoy the cluster of sun grazers, then ask for orbital fits with uncertainties and for any compositional clue that ties them to our main character. The moment those lines cross, you will not need breathless narration. The measurements will be interesting on their own. Until then, coincidences deserve a smile and a measured shrug. The sky is busy, detectors are imperfect, human pattern hunger is endless. 3i Atlas already gives us enough real puzzles to solve without importing extras from the rumour mill. If any of these side stories grow into evidence, we will know, because the numbers line up, the geometry behaves, and independent eyes agree. Line up the travellers and watch how our confidence bends. The first interstellar visitor we met in modern times slid through the inner system without a visible coma, then nudged its own path ever so slightly, as if pushed by an invisible hand. No roaring jets, no dusty tail. Just a tiny non-gravitational drift that refused to be comfortingly boring. The second visitor felt like a sigh of relief. It wore a classic coma, shed gas and dust in familiar ratios, and behaved the way a textbook comet behaves. Now comes 3i Atlas, which seems determined to reverse the rules with a sunward-leaning feature and chemistry that does not sing the usual water-led melody. This trio matters because it exposes the trap of small samples. With one object, you tell a just-so story. With two objects, you claim a pattern. With three, you feel the edges of a family. and the edges do not match the neat labels you hope to reuse. The first traveler teased ideas like thin sheet geometry or exotic ices that evaporate without leaving a bright cloud. The second reassured us that not every messenger from the wider galaxy is a riddle. The third yanks us back into the deep water, where nickel rises early, carbon dioxide runs hot, and a narrow plume seems to ignore the breeze for a precious inner span. Seen together, the visitors sketch a motif of reversal. One looked like a rock yet behaved like a comet in its motion. One looked and behaved like a comfortable comet from home. One looks like a comet, yet tries to point a line toward the sun and speaks in a metal voice before iron answers back. If the galaxy sends 1,000 such objects past us, perhaps these three will settle into a broad distribution where our local expectations are merely one hill among many. If the sample stays sparse, the oddballs carry more weight than they should. Either way, the smart move is to widen our models rather than squeeze the facts into the boxes we already own. What would widening look like in practice? First, we decouple appearance from propulsion. Outgassing can be faint or invisible, and still push on a body if the gas is clear and fast. A thin sheet can feel radiation pressure more strongly than a lumpy rock of the same mass. 3i Atlas adds a fresh line to that page. A focused vent that briefly holds a direction near the sunline may exist even while the far field obeys the usual tail geometry. Second, we loosen our grip on local chemistry. Interstellar nurseries can pack volatile inventories that do not map cleanly to our own. What feels rare here may be routine there, and layered structures that seem unlikely in our comets may be common products of different thermal histories. Third, we accept that sample bias is loud. We are most likely to notice interstellar visitors that do something dramatic near the sun because drama is bright. Quiet rocks pass in the dark and slip away uncounted. That means the early roster will overrepresent the unusual. It is not a conspiracy. It is the physics of discovery. The cure is time and deeper surveys that catch the faint and the dull as well as the flashy. Where does this leave the story we are telling right now? Not with a tidy label, with a sharper question. Are we watching three exceptions in a small class that mostly behaves, or are we catching early glimpses of a population where diversity is the rule? The first answer is comforting. The second is richer. It would mean our home system taught us true things that are not universal, and that the galaxy's debris carries recipes from many kitchens. For the audience, there is a practical payoff to this humble posture. It keeps us honest when updates arrive. If the sunward filament softens under better geometry, we do not lose the plot. We fold the result into a larger lesson about projection and processing and keep looking. If the filament hardens and the chemistry holds, we do not shout, miracle. We trace the line that links these three visitors into a framework that pairs natural mechanisms with new boundary conditions. In short, these travelers do not divide into normal and weird. They map the space between those words. One challenged motion without a visible coma. One matched our expectations. One challenges geometry and chemistry at once. That spread is not a failure of explanation. It is the beginning of a real catalogue. 3i Atlas is not obligated to act like a comet born here. Our job is not to insist that it should. Our job is to listen, measure, and let the family portrait grow stranger and truer as the gallery fills. When people imagine comets, they picture dramatic streamers stretching across the sky, a glittering dust tail, and a razor-straight iron tail that point away from the sun like banners in a gale. 3i Atlas refuses the postcard. The coma glows, yes, but the tail structures are muted and asymmetric. Polarization measurements how light is oriented. After it scatters off dust, add another odd note with a deep negative branch where we would expect a gentler dip. Put those pieces together, and you get a dust story that does not match our usual recipe. Start with what polarization says in plain language. Sunlight is unpolarized when it leaves the sunday. After it bounces off small grains, some directions of vibration are favored. Measure that preference, and you learn about grain size, texture, and composition. Comets from our backyard tend to trace a familiar curve as viewing angle changes. A strong negative polarization, especially at certain angles, hints that grains are either unusually fine, strangely shaped, coated with odd material, or clustered into fluffy aggregates that make light dance in ways our models rarely require. Now add the missing drama of the tails. A bright coma with short or subdued tails tells us dust is not flying far. That can happen if the gas flow is dense but slow, if the grains are large and heavy, or if the dust-to-gas ratio is out of balance so the coma looks fat, while radiation pressure and the solar wind fail to pull long streamers free. In that case, the dust hangs close, rounding the inner glow but refusing to paint a sweeping arc across space. It is a quiet rebellion against the picture books. Asymmetry ties the room together. Instead of a neat, round haze around the nucleus, one side of the coma bulges. That can be a vent carving a fan. It can be the shadow of terrain shielding part of the flow. It can be a projection effect that piles brightness on one side from our angle. The key is to watch whether the bulge rotates or stays put. A rotating fan points to a spinning source. A fixed bulge suggests steady geometry or a persistent terrain effect. The early reports favour stubbornness. The bulge prefers the same quadrant, which pairs suspiciously well with the sunward filament. What kind of dust makes this portrait? Fine grains scatter light differently from pebbles. Fluffy aggregates scatter differently from compact glassy shards. Coatings of organics or metals change how light reflects and polarizes. If carbon dioxide-led gas is entraining a different size distribution than water-led gas would, the coma will announce that in both its shape and its polarization. Heavier grains hug close. Strange coatings deepen the negative branch. Fluffier clusters can produce strong polarization effects while still being carried. Short distances before disintegrating. There is a clean way to probe these ideas. Map polarization across the coma, not just as a single number. If a narrow ribbon traces the same path as the suspected filament, with polarization values that mark gas-rich flow and unusual grain properties, then geometry and dust physics join hands. Take simultaneous spectra and measure dust color, how brightness changes with wavelength along and across that ribbon. Larger grains tend to produce flatter colors. Fine grains and certain organics tilt the spectrum. These maps can tell whether the plume carries a special cargo while the surrounding coma stays generic. Consider also the ion tail, the usually straight bluish companion to the dust tail. If it is weak or absent, there are two simple readings. Either ion production is low because neutral gas is not being ionized efficiently, or the viewing geometry and solar wind conditions are unkind. Magnetic draping measurements from space would help here. A weak or symmetric drape argues for low ion production and a quiet tail. A skewed or strong drape even without a visible ion streamer would mean the tail is there, just hiding in brightness limits, and the plasma still feels its pull. What would push us away from exotic dust stories? If deeper imaging under darker geometry reveals long tails after all, the early muting was a sensitivity issue, not physics. If polarization curves relax toward the ordinary when measured with better precision, the deep negative branch may shrink into the noise. If the coma asymmetry swings with viewing angle, projection earns a medal and the plume loses its special status. But if the coma stays lopsided, the tails stay short, and the polarization map draws a line where the plume lives, then dust is not just a passenger in this saga, it is a narrator. It tells us that the grains around 3I Atlas are not standard issue, that the gas pushing them is not behaving like water-led flow, and that the focused feature can carry dust briefly against our expectations before the sky's steady forces reclaim it. When light whispers in polarization and tails refuse to pose for the camera, that is not a failure of spectacle. It is a clue that the physics in the inner coma is playing a different tune and inviting us to learn the steps. Space is not empty. It is a river of charged particles flowing outward from the sundae. That river is the solar wind. When it slams into an active comet, the wind wraps around the cloud of gas and dust like water around a boulder. Magnetic field lines bend and stretch. Ions are picked up and carried away. If you could see the fields like glowing threads, you would watch them drape around the coma in graceful arcs. That drape is a fingerprint of how much gas is being shed and how easily it becomes ionized. Here is the plain version. Neutral gas near the nucleus gets blasted by sunlight and high-energy particles. Some molecules lose electrons and become ions. Ions feel magnetic fields, so the solar wind grabs them and yanks them downwind. Instruments on spacecraft can count those ions and sort them by mass to charge. Water group ions weigh one thing. Carbon monoxide and carbon dioxide weigh another. Metals like nickel or iron show up as heavier outliers if they are there in real amounts. The detector reading is not an opinion. It is a tally of what flies into the instrument. Magnetometers add the map that our eyes cannot draw from Earth. They sit on a boom and record the exact direction and strength of the magnetic field. As the wind flows past a comet, the field lines bend into a pattern that tells you about the size and vigor of the ionized cloud. If the outgassing is strong and easy to ionize, the drape starts far from the nucleus and the bend is pronounced. If outgassing is weak, the field hardly notices. A lopsided source can even skew the drape toward one side. That would be a subtle sign of a directional plume written right into the field. Why is this powerful for 3I Atlas? Because the ground story says carbon dioxide leads, water lags, and metals behave oddly. If that is true, the river should taste different. The ion mix should lean hard toward carbon dioxide ions. Water ions should be fewer than usual for a bright coma. If nickel really escapes into the gas, a faint but real heavy ion signal could show up above background. The field drape might also tilt toward the same quadrant as the suspected sunward filament. 4 different senses would then be telling the same tail images: spectra, particles, and fields. We can sketch clean expectations without jargon. If a spacecraft crosses the ion tail, detectors should see counts rise from nothing to a plateau, then fall back to nothing. Inside the plateau, carbon dioxide ought to dominate. If the crossing happens near a pulse in activity, the counts could rise and fall on the 4-hour beat. A phase match between particle data and the light curve would be a gift. It would tie the inner engine to the river far away. There are ways this could disappoint without killing the mystery. Distance matters. A tail is a ribbon in a vast volume. Miss by a little, and you miss by a lot. The solar wind is gusty too. A coronal mass ejection can crash the party and stir the plasma into a mess that hides delicate signatures. A null result under noisy wind does not tell us much. A null result under quiet wind and good geometry bites harder. That is why teams watch the sun's weather before they claim victory or defeat. Plasma physics also helps check the sunward line itself. A tight, focused outflow near the nucleus makes ions in a narrow zone. As they are picked up, their paths should first fan outward in a predictable arc. With careful modelling, you can project that arc into the plane of the sky and compare it to the imaged filament. Agreement would not prove cause, but it would make a neat triangle with chemistry and geometry at the other corners. Disagreement would force us back to the drawing board. The best part of this approach is that it is honest to the strengths of each tool. Images show shape but invite illusions. Spectra reveal molecules but not motion. Particle detectors measure what is truly there in the wind. Magnetometers feel structure without caring about brightness at all. When all 4 agree, even roughly, belief hardens. When they split, you learn which parts of the story were wishful thinking dressed as certainty. So the next time you see a tidy line on a processed image and someone whispers artifact, remember that space has other ways to speak. If the river bends and the ion recipe tilts in the same direction, the camera pointed, a thin plume leaning into the light becomes less of a photographic dare and more of a physical fact. If the river stays straight and bland while the pictures grow dramatic, we step back and ask who to trust. Either way, the solar wind is the fairest judge we have, and it is about to enter the courtroom. There is more data than any one team can read with human eyes. Images from many nights, spectra stacked into time series, polarization maps, spacecraft particle counts, magnetic field traces. Buried in that mountain could be the one connection that makes the puzzle snap into place. This is where we let algorithms do what they are good at, not to replace judgment, but to widen our reach. Let the machines hunt for patterns we are too slow or too biased to see, then make those patterns fight physics in daylight. Start with a simple goal the audience can feel. We want to know whether the 4-hour heartbeat lines up with anything else. Feed the light curve, the estimated filament brightness, and the strength of specific spectral lines into a search that does not care about our favourite explanation. Ask whether nickel brightens when the plume sharpens. Ask whether carbon dioxide peaks half a phase before the visible jet. Ask whether water rises only, after both, as if deeper layers opened late. These are yes or no questions that a machine can test across thousands of combinations without getting bored. The trick is to avoid teaching the answers we want. Algorithms are eager students. If you train them only on comets from our backyard, they will flag everything about 3i Atlas as weird by default. So, we balance the set. Include comets with odd polarization. Include those with short tails and large grains. Include high carbon dioxide cases. Then let the system build a map of what normal covers and what it does not. When 3i Atlas lands outside that map on a particular axis, say nickel behavior versus distance from the sun, you learn where the true novelty lives, instead of treating every difference as important. Noise is not the enemy if you are honest about it. A robust approach slices the data in many ways and looks for signals that survive. Shuffle the timestamps to break fake periodicities. Mask parts of the coma to check whether a filament signal vanishes when you remove the pixels where it lives. Swap in reductions from other teams and see if the pattern holds. Real relationships persist through these indignities. Coincidences evaporate. Machines excel at this kind of ruthless repetition, while humans tire and cut corners. There is a class of patterns humans rarely spot at first glance lagged relationships. Maybe the nickel line peaks, then 2 hours later the visible filament sharpens, then 2 hours after that water climbs. A human eye sees noise. A cross-correlation can reveal a staircase. If that staircase repeats across nights, it whispers mechanism. Perhaps different volatiles vent in a sequence as the surface rotates through sunlight, or as a subsurface pocket fills and vents. The important part is not the software, it is the testable schedule that falls out. Once you have it, you can point telescopes at the right hour and ask the sky to confirm or deny. Another machine-friendly quarry is spatial pattern. Polarization maps, color maps, and spectral slices can be turned into grids and compared pixel by pixel against the filament's path. If a ribbon of high polarization, a ribbon of carbon dioxide enhancement, and a ribbon of nickel all trace the same curve within uncertainties, that is a geometric handshake. If the ribbons miss each other, we may be stacking unrelated quirks into a story they do not support. An algorithm can compute the overlap honestly and return a score instead of a hunch. Of course, there are traps. Overfitting is the classic one. Give a flexible model enough knobs, and it will fit the noise until it sings. The cure is to hold out data the model never sees. Train on August, test on late September. Train on one telescope, test on another. Do not celebrate until a pattern survives that harder exam. The second trap is p-hunting, chasing any tiny effect that crosses a threshold. Beat that by declaring the few relationships you care about in advance and letting the rest go. The payoff of this hybrid approach, human questions plus machine stamina, is a cleaner narrative. Either we discover that the heartbeat, the plume, and the chemistry move together in a disciplined way, which makes the natural nozzle plus layered ice model more compelling, or we find that nothing lines up and our favorite ideas wobble. Either way we win. We trade speculation for prediction. The audience gets a front row seat to a process that is humble enough to be wrong and ambitious enough to learn fast. So, let the machines chew. Let them scan the haystack for threads that weave images, spectra, and plasma into one cloth. Then we, not the code, decide which threads make physical sense and which are pretty tangles. If the patterns survive fresh nights and new instruments, belief earns a backbone. If they do not, we thank the algorithms for saving us months of chasing ghosts and get back to work with clearer eyes. Every field has its year, when the walls creak. This year feels like that. In energy labs, tiny stars blink to life and keep doing it, not once, but again and again. In city basements, quantum messages leap across ordinary fiber, like secret handshakes riding the same cables as your streaming shows. In deep time, telescopes stare at baby galaxies and find black holes that look too big, too early, tugging at the story of how structure formed. None of these headlines prove anything about 3i Atlas. They do something subtler. They reset the burden of imagination. When fusion ignition repeats, it tells us persistence turns impossible into procedure. You push lasers a little cleaner, shape targets a little smarter, and the physics that used to be a party trick becomes a platform. That lesson matters here. A single strange plume is a party trick. Reproducible geometry, correlated chemistry, and matching plasma signatures are a platform. If we can make this comet's weirdness repeat under better control, it graduates from rumor to result the same way a fusion shot does when it lights more than once. Quantum teleportation across city-scale fiber is another soft nudge. It is not faster than light mail. It is a promise that fragile correlations can be preserved across noise if you build the right scaffolding. Astronomy has its version of that scaffolding: cross-instrument campaigns, shared calibrations, pre-registered predictions. When those pieces lock together, subtle signals survive the chaotic weather of space and the biases of teams. The 4-hour heartbeat, the nickel-first chemistry, and the sunward filament will either hold under that stress or they will crumble politely. Either outcome is progress. And those early universe puzzles, black holes that look fully grown in a toddler cosmos, remind us that our neat sequences may be local myths. We thought galaxies grew, then black holes. The sky whispered maybe the holes came first, and galaxies gathered around them. That reversal motif rhymes with our comet trio. One visitor challenged motion with no visible outgassing. One behaved like home. One challenges geometry and chemistry at once. Maybe our rules for small icy bodies near stars are local myths too, true in our backyard and incomplete in the wider neighborhood. None of this is license to hype. It is permission to ask better questions and to build sturdier bridges between ideas. Fusion labs make their milestones by publishing shot plans and then hitting them. Quantum teams publish error budgets and then beat them. Cosmology groups post curated data releases so others can poke holes. Our comet story deserves the same spine. If we say the plume should brighten at a particular phase, we show the schedule and the threshold. If we claim carbon dioxide dominates, we stack spectra from many nights and annotate the lines. If we predict a skewed magnetic drape, we mark the time window when a spacecraft will cross and agree on how we will call it if the wind is noisy. There is also a psychological payoff to framing the comet inside this larger year. It inoculates us against the addiction to single-bullet explanations. The world rarely changes because of one dramatic figure on one dramatic night. It changes because many small, disciplined measurements start pointing the same way. 3i Atlas does not need to carry the burden of rewriting comet physics alone. It needs to hold its shape while other instruments take turns poking it. If it does, textbooks add a page. If it does not, we keep the page blank and thank the process for saving us from ourselves. So here is the healthy way to enjoy a year of strange signals. Hold two thoughts at once. Nature is more generous and weird than our models, and our job is to earn every inch of belief with tests that bite. Do not let the thrill of fusion or teleportation bleed into this story as borrowed credibility. Let them serve as reminders that patience and design beat breathlessness. If 3i Atlas wants to join the club of 2025's rule benders, it knows the cover charge. Be repeatable, be multi-sensed, be falsifiable, and survive. If it pays that price, we will all see the receipt together. Enthusiasm without brakes turns science into a rumor factory. We are not doing that. We are going to build guardrails so the ride stays fast and honest. The simplest guardrail is language. Say what we know, what we think, and what we are merely imagining in that order. Use words that scale with evidence. Might, hints, and suggest belong to early nights. Indicates, and consistent with arrive after replications. Requires and rules out are for the rare days when the numbers corner us and the old story breaks. Next, guardrail, pre-commitment. Before new data land, we write down clear predictions and how we will count a hit or a miss. If we say the plume should peak at a particular rotation phase, we state the phase window and the contrast we expect above background. If we say carbon dioxide will outrun water by a certain factor, we fix that factor and the uncertainty we will accept. Then we publish those lines so anyone can hold us to them. This kills the temptation to move goalposts after the whistle blows. Guardrail 3 is pluralism in tools. Images are seductive. They can also lie. So every geometric claim must face at least one non-image witness. A plume that looks narrow in pictures should leave a ribbon in polarization, a chemical gradient in spectra, or a skew in magnetic draping. If a feature lives only in one sense, skepticism gets first chair. If 2 or 3 senses sing the same melody, confidence climbs naturally without chest beating. Guardrail 4. Independent pipelines. Give the same raw frames to multiple teams and let them process in public. Different point spread functions, different background treatments, different star rejection strategies. If a feature survives those variations, it has earned a louder voice. If it vanishes in one or more pipelines, we do not average the truth. We figure out why. Maybe a setting over sharpens, maybe another undersuppresses noise. Either way, the lesson improves the next round. Guardrail 5. Null results get equal billing. A night with no filament at the predicted phase is not a failure to hide. It is a constraint. It narrows the model. Perhaps the vent stalled. Perhaps the geometry killed the contrast. Perhaps the plume was a ghost. Reporting the zeros prevents confirmation bias from painting every silence as uninteresting. A graph with flat lines is as valuable as a graph with spikes when you are testing a heartbeat claim. Guardrail 6. Base rates and priors. Extraordinary does not mean impossible. It means rare given what we already know. We set our belief dial using the frequency of similar events. How often do processing artifacts masquerade as jets? How often do carbon dioxide-dominated comi occur? How often do 4-hour light curves mislead? We do not let a single spectacular frame overwhelm those priors. Instead, we require enough counterweight independent confirmations to justify turning the dial. Guardrail 7. Resist tidy narratives. Humans love a single-cause story. Nature prefers layered explanations. If a nozzle plus rotation plus carbon dioxide chemistry together explain the filament, that is not messiness. That is realism. We do not amputate parts of the mechanism to tell a cleaner tale. We explain the stack, show the predictions each layer makes, and accept that some mysteries resolve into harmonies, not solos. Guardrail 8. Time boxing hype. Give every hot claim an expiration date. If the test window passes without the predicted signal, the claim downgrades automatically until new evidence arrives. This protects us from evergreen speculation that lingers for months and crowds out better work. The comet is moving. Our confidence should move with it. Finally, Guardrail 9. Transparency about temptation. If an engineered alloy thought, the experiment fires the imagination. We say so, and we say the specific signatures that would have to appear before we let that idea drive. Isotopic ratios. Industrial byproduct molecules with no clean natural path. Geometric edges too straight for rubble. Without those, the idea stays in the library, not on the stage. These guardrails are not mood killers, they are trust engines. They let us push hard without sliding into storycraft. They keep the investigation thrilling because every constraint, every replication, and every null sharpens the edge of what remains. If 3i Atlas turns out to be a masterclass in mundane physics wearing strange lighting, great, we will have learned how to avoid being fooled next time. If it keeps passing tests and stacking independent signatures, even better, we will have earned a new page in the rules without leaving skid marks. Curiosity stays hot, hype stays leashed. That is how a science news magazine deserves to run. Here is the simple map for what happens next. Draw 3 columns in your mind: images and timing, chemistry and space plasma. In each column, there are clean forks where the story splits. We are going to walk those forks so you can tell, in real time, which path we are on without waiting for anyone's hot take. The goal is to make you your own analyst when the next data drop lands. Start with images and timing. Fork 1 is the 4-hour heartbeat. If the filament brightens at the same phase across multiple nights, rotation wins, and a physical vent becomes the favorite engine. If the phase wanders without pattern, rotation loses power, and projection or processing climb. Fork 2 is geometry. As Earth's view changes and telescopes roll, a real plume keeps roughly the same sunward stance, while a projection trick slides in a predictable arc. If a Mars angle image appears and shows a matching sunward preference, that is a major branch toward reality. If it shows symmetry, the filament downgrades. Shift to chemistry. Fork 3 is carbon dioxide versus water. If carbon dioxide lines stay dominant while water lags, the carbon-led engine holds and helps explain heavy, short-lived dust. If water catches up rapidly without a distance threshold, the early imbalance softens. Fork 4 is nickel versus iron. If nickel continues to appear before iron with a sharp distance switch, layered structure, or unusual compounds remain in play. If iron turns out to be present all along once sensitivity improves, the exotic metal story quiets. Most decisive would be spatial gradients if spectra taken along the filament show a distinct ratio from the surrounding coma, chemistry, and geometry locked together. Now, the space plasma column. Fork 5 is the ion recipe, a crossing that detects a strong carbon dioxide ion fraction, with water ions suppressed, aligns with the ground story. A normal recipe pulls us back toward ordinary comet behavior. Fork 6 is magnetic draping. A clean asymmetric bend in the field that leans toward the suspected plume side is a second witness to directional flow. A flat, symmetric drape under quiet solar wind conditions argues against a focused channel. If particle counts or field bends line up in phase with the 4-hour beat, rotation ties all 3 columns together. There are global outcomes that fall out of these forks. If images phase lock, chemistry shows spatial gradients, and plasma matches the skew, we move to a high-confidence conclusion. A focused vent on a layered carbon dioxide-led nucleus created a narrow inner plume that appears to lean sunward before the wind takes over. That is not magic. That is a boundary case most textbooks never pictured. If, instead, the filament refuses to phase lock, spectra look the same inside and outside the line, and space sees a bland tail, the artifact and projection camp takes the lead. The result will still be valuable, because it nails down how far image processing can push a real but soft asymmetry into a misleading pencil line. There is also a middle branch we should respect. Some forks may split, a faint phase lock might exist, but the chemistry could be less skewed than early frames suggested. The plasma might show a mild asymmetry without a clean beat. In that world, we accept that nature stacked several ordinary effects at once: a nozzle, a certain dust mix, and a viewing geometry to imitate a bigger surprise. The right response is to publish the thresholds at which the imitation becomes convincing, so the next time we spot the same stack, we recognize it faster. What should you watch, practically? Look for published phase curves with clear bins, not cherry-picked frames. Look for spectra plotted along slits that cross the filament, not averages over the whole coma. Look for spacecraft plots marked with solar wind conditions and confidence intervals. When you see a claim, ask what fork it passed and whether the other columns agree. That is how you will know whether we are closing in on a new page in the rules, or learning, once again, how easy it is for bright fog and clever math to fool us. Whichever branch wins, we will chart it openly. If tests fail, we say it and move the idea to the bench. If they pass, we raise the bar and try to break the success with harder versions. That is the decision tree. It is not dramatic. It is decisive, and it turns a viral mystery into a shared, measurable investigation you can follow with confidence. By now, you can feel what this object has already done. It made us slow down and separate picture from physics. It forced us to write predictions we could miss in public. It reminded us that wonder is not the opposite of rigor. It is the reward for rigor when the sky keeps surprising us. Whether the sunward filament survives or dissolves, that lesson is already in the bank. If the focused plume holds, if carbon dioxide keeps leading, and nickel keeps speaking first, we earn a new boundary case for small, icy, bodies near stars. Textbooks will add a paragraph that says, a narrow vent on a layered nucleus can briefly push a line against the breeze before the wind wins. They will show how gas composition shifts dust behavior, how rotation turns vents into metronomes, and how magnetic draping can sketch a flow you cannot see with light alone. That is not a revolution. It is a refinement that makes our models more honest and our expectations less parochial. If the plume softens under better geometry, if spectra flatten across the line, and if space finds a normal ion recipe, we still win. We will tighten our tools so the next interstellar visitor is harder to misread. We will publish processing settings that are safe and those that are spicy. We will teach our eyes to distrust pencil lines that do not earn a second witness. The next time a soft asymmetry tempts us, we will remember the cost of falling in love with contrast and do the slower thing right away. Either way, 3i Atlas rewired something more important than a model. It changed how we perform curiosity under pressure. We invited defeat on camera and treated null results as plot points instead of embarrassments. We treated wild ideas as laboratories with safety rules, not as clickbait. We shared the calendar of tests so anyone could play along. That is how a science news magazine ought to run when the sky throws a curveball. Fast, yes, but with breaks that work. There is a human thread running through this too. We want stories that end with certainty. The universe prefers chapters that end with better questions. Today we have sharper ones. What recipes from other star nurseries show up in our neighborhood? How often do carbon-lead comae appear? When do layered nuclei carve disciplined jets? How does the solar wind write those decisions into the magnetic field for us to read? Those questions do not shrink the wonder. They give it edges you can hold. So keep watching with us. When a new frame drops, you know which forks to check. When a spectrum appears, you will know which lines to find. When a spacecraft graph scrolls by, you will read the river as easily as a weather map. And when this visitor fades into the dark, as all travelers do, you will be ready for the next one, with a steadier hand and a wider map. Curiosity brought you here. Discipline keeps you here. The universe will handle the rest. Whatever 3i Atlas turns out to be textbook honest or rule-bending, it already did its job. It made us look harder, think cleaner, and leave room for wonder without letting the wind blow us over.